All right, let's move. Board exams love to trap you with mixed acid-base disturbances. Why? Because it's the perfect place for one critical problem to hide another.
You're looking at a complex case precisely because one primary diagnosis is masking a second, even a third. And without a rock-solid algorithm, you're going to miss it.
So for every single case of metabolic acidosis, you must, I repeat, you must execute this two-step process. No exceptions.
Step 1, Winter's formula. Its sole mission to predict exactly what the lungs should be doing to compensate.
The formula is expected PCO2 equals 1.5 times bicarbonate plus 8 plus or minus 2. If your measured CO2 is higher than what you calculated, you've got a second problem, a respiratory acidosis. If it's lower, you've got a respiratory alkalosis. Simple as that.
Now for step 2, the delta-delta ratio. This is your high-yield weapon for finding the metabolic problem hiding inside your first diagnosis.
The formula is the change in the anion gap divided by the change in bicarbonate. Now listen up. A ratio greater than 2 means there's a hidden metabolic alkalosis. A ratio less than 1 unmasks the hidden normal gap acidosis. This is how you find what's hiding. Let's go!
Before we proceed, the mandatory medical disclaimer. This content is for educational purposes for international boards only. It is not, under any circumstances, medical advice. Always consult official guidelines and a specialist physician for any and all clinical decisions.
Okay, in the real world, especially in the ICU, a patient rarely walks in with just one pure, clean disturbance. So let's really decode these formulas and move from just the what to the crucial why.
So let's start with a foundational question. You've got a patient, you've identified a high anion gap metabolic acidosis. Why is Winter's formula the absolute non-negotiable next move?
Because it defined normal respiratory compensation. The formula, 1.5 times the measured bicarbonate plus 8, gives you a number. It tells you exactly what the CO2 should be in a perfect compensatory state. You cannot guess. You have to do the math.
And this right here is the whole game, the gap versus gas battle. If the patient's actual CO2 is higher than what your formula predicted, their lungs are failing them. That's a secondary respiratory acidosis. If their CO2 is lower, they're blowing off way too much, a secondary respiratory alkalosis.
Okay, let's move on to the really high-yield calculation for your top-tier exams, the delta-delta ratio. But you might be thinking, why do we even need this if we already know there's a high anion gap? Because a high anion gap can hide other metabolic problems. And that's the key takeaway. Relying only on the anion gap is a classic rookie mistake. It's not enough.
So here's the physiological baseline you need to know. We expect a perfect balance. For every 1 point that the anion gap goes up, the bicarbonate should drop by 1 point. That sets our gold standard, a 1-to-1 ratio.
And this table just lays it all out beautifully. If your ratio is greater than 2, it means the bicarbonate is too high. It's higher than it should be. Why? Because there's a hidden metabolic alkalosis, maybe from vomiting. But if the ratio is less than 1, the bicarbonate is too low, and that unmasks a hidden normal gap acidosis, maybe from something like diarrhea.
Now, let's put it all together in a classic scenario. Imagine a patient with chronic COPD who develops DKA and then starts vomiting. You've got a primary respiratory acidosis, a secondary high-gap metabolic acidosis, and a tertiary metabolic alkalosis all at once. Their pH might look deceptively normal, but without these formulas, you'd never uncover the 3 life-threatening problems happening simultaneously.
Okay, you understand the logic. Now we need to encode it so you can recall it instantly under pressure. We're going to lock it in with a quick chant. Ready?
Winter's for the lungs.
1.5 plus 8.
Delta, delta for the gap.
1-to-1 is pure.
Greater than 2, alkalosis, hide.
Less than 1, nagma, inside.
All right, now for our question of the day, let's bring this to the bedside. Have you ever actually used the delta-delta ratio to uncover a hidden alkalosis in a complex patient, maybe someone with uremia or sepsis? Finding that can completely change your management. Let us know what you've seen in the comments.
Excellent work. You have now decoded the math behind the mixed acid-base storm. Just remember, Winter's is for the lungs and delta-delta is for the gaps. In our next explainer, we're putting the arterial blood gas strip right in your hands. So join us for our next mission, ABG Workshop. Master arterial blood gas in 5 seconds. That's board exam gold.